Hello everyone. So welcome back to our latest lecture session. So again we'll have our brief summary of what we discussed in the last lecture class, right? So we are talking about alkalinity and we looked at it in terms of the acid neutralizing capacity and in general because the natural systems only contain or usually not only contain, I guess, the predominant acid base system is the carbonate system. We usually define the theoretical alkalinity in terms of the carbonate species and calculate the amount of acid that would take to neutralize the relevant deprotonated forms of your particular carbonate system, right? And that is why we end up titrating it to 4.5. And when would your theoretical definition of alkalinity be at odds with what you would measure practically by titrating with the acid in the lab, I guess, right? When you have other relevant acid base systems, with pKa values greater than 4.5, right, which can again consume or neutralize some of your acid. Yes, in that case, again we looked at the relevant aspects in detail, so we won't go into that further. And then we start discussing about acidity, right? So alkalinity is about the acid neutralizing capacity of your particular solution, and acidity will obviously give an idea about the base neutralizing capacity of a solution. Anyway, acidity is not rarely, I guess, less widely used or applicable when compared to alkalinity, which is used everywhere in almost all your relevant calculations. So again, we are going to go through and look at acidity right now, right? So acidity, right, we start discussing about that we say is equal to or similar to the base neutralizing capacity. Yes, that's something we discussed. And I believe in the last class we also talked about that unlike alkalinity, we have three kinds of acidity that people look at. One is the one which you would look at the mineral acidity, right? And next we look at phenolphthaline acidity, and this I believe is also called methyl orange acidity, right? Based on its the type of indicator that you are using, again phenolphthaline acidity based on the type of indicator that you are using, and then total acidity. And depending on the textbooks that we or you are going to look at, let's say people sometimes think of phenol acidity too as total acidity, but there are three distinct kinds of acidities, right? And we are going to look at each of them in greater detail, right? So again, acidity is nothing but base neutralizing capacity, right? So you're let's say in the lab, how would you measure that? You're going to take a base of known concentration in your particular burette and keep titrating that against your solution until you reach an equivalence point, right? And what is this equivalence point about? When the amount of base in this case added is equivalent to the amount of acid initially present in your solution. But obviously if it is diprotic or triprotic system, you are going to have multiple equivalence points, right? So again here looks like we are going to look at three equivalence points. So let's look at what they are in greater detail, right? So first case is when we look at mineral acidity or methyl orange. So in, the equivalence point we look at is 3.7, and we will see why 3.7. We will go back to that soon, right? And what else here, please? So here what are we trying to measure? What are we trying to measure here, right? It measures the strong acids. It measures the strong acids present in the solution, right? It will give you an idea about only the strong acids present in the solution. So the key here is that strong acid. So H2CO3 with a pKa of 6.3 and the pKa2 of around, what is it now, 10.3. We don't call that a strong acid, but HCl, HNO3 and so on, we look at that in terms of strong acids because of their low pKa values and ability to donate the proton or deprotonate even at low pH values, right? So this particular mineral acidity or methyl orange acidity can or is only trying to calculate or measure the amount of these strong acids present in your solution, right? So let's look at why pH 3.7 now, right? The key is that it only wants to measure the strong acids and not the H2CO3 that's present in your system, right? Let's look at obviously the relevant carbonate speciation system. So this is something that we looked at previously too, right? I believe we looked at this with respect to Wiemann and developing it for alkalinity. So I believe the total concentration we have is 0.01 molar, and we have the figure where x-axis is pH and y-axis is concentration. So now I only want to measure the strong acids, right? Obviously the key is then the pK is going to be low, and obviously I do not want to measure the amount of H2CO3 present, right? So what is that now? So as we see, it was around 3.7. What was that? The equivalence point, right? And as you can see from here, at 3.7, let's say a pH of 3.7, what do you see here? H2CO3 does not start dissociating yet, or any base, if any base is added to your solution, will H2CO3 be able to neutralize that at until the pH of 3.7 or in this region? No. Why is that? As you see in this entire region until 3.7, H2CO3 does not dissociate into H plus and HCO3 minus, right? So obviously if I am not trying to measure H2CO3 but only trying to measure the strong acids, which region will I, until what pH will I titrate to? Until that pH when H2CO3 is not going to dissociate, and that, as you see, is around 3.7, and that is the reason we end up measuring or having an equivalence point. Equivalence point is 3.7 for your mineral acidity, right? So that is the key here, that we are not trying to measure the H2CO3 but only the strong acids. That is one particular case, yes. So let us move on to the next particular aspect, and here again one way to understand this is your reference is H2CO3, right. So looks like I missed writing down the relevant equation, we will come back to that. So keep in mind that if you are trying to write down the component balance and understand it in terms of H total, if you have the reference or your one of the components as H2CO3, you will be able to write the relevant equation. So obviously I missed writing the relevant equation, so we are going to go back to that, right. So we understood how, and so here in this case acidity is going to be equal to what now? First we are going to write down all the acids present, so only strong acids, so that will be only in the form of H plus in this case, right. And then again the case we are considering is when we have only the carbonate system here, and obviously any other strong acids present are going to dissociate, right. So we are going to have H plus, and we obviously need to subtract all these bases here, right. So it is going to be obviously OH minus here, right, minus, and what other bases do we look at here? We obviously look at CO3 2 minus, in this region, this is CO3 2 minus and HCO3 minus, and obviously HCO3 minus can consume 1 proton, so we are going to have a coefficient of 1 for it. CO3 2 minus can consume what do we say, 2 protons, right, and the reference is with respect to H2CO3, yes, and that is why we are going to have coefficient of 2 here. So it is going to be minus HCO3 minus 2 times of CO3 2 minus, right, and obviously what are the units here, because we already looked at the relevant coefficients here, right. The units are not equivalents per liter but moles per liter, yes. Again the units for this particular these particular variables 1, 2, 3, 4 are moles per liter, and you will end up with acidity in terms of equivalents per liter, right. Again to understand this, we mentioned that we can look at the system with respect to H plus and H2CO3 as our components. So what is the relatively unique aspect here? Usually if you remember, whenever we analyze the system we take H plus and the most deprotonated form, which is CO3 2 minus, as our components, but because our reference, right, we are trying to not measure H2CO3 and the reference here is H2CO3, so we are going to try to look at the system in terms of H2CO3 and not CO3 2 minus. So if that is the case and I write down H total, right, or let me just plug this in here, not plug this in, write it down in the form of tableau. So what are the species that you would expect? H plus, OH minus, we are not going to write H2CO3 because that is not something we are measuring here, right, HCO3 minus, or even if I write that, let us see why we do not need that, H2CO3, and here again H2CO3 total, H2CO3 and CO3 2 minus. So how many H plus do I need? So I am going to have 1, and how many OH minus? Minus 1. HCO3 minus, how do I form that? By H2CO3 minus H plus, right, and that is the reason why we end up with minus here again. And how do you form H2CO3? By 0 and 1, and CO3, how do you form that? By 1 H2CO3 and minus 2 H plus, right? And more or less if you look at it, that's H total, and that's similar to your acidity, right? When is that now? H total is equal to acidity when you choose H plus and H2CO3 among your components, right? So that's for sake of your understanding here. So again, what are we measuring here? We are only measuring the strong acids, which will be in the form of H plus, and obviously we need to subtract the other bases, which in this case we are only assuming HCO3 minus and CO3 2 minus. And why do we take the coefficient of 1 and 2 here? Because CO3 2 minus can neutralize 2 protons before moving on to its protonate state, which is H2CO3, and HCO3 minus can take 1 proton. So that is the case, we have the relevant coefficients here. So until now we looked at mineral acidity and obviously pH 3.7. So let's move on to the next case, I guess, right? So next case obviously is phenolphthaline acidity, again based on the indicator that we look at. So obviously the pH we are looking at is 8.3, and again let's see why. So in this case, what are we trying to measure with this particular acidity, I guess? When you titrate the system with a base until you achieve a pH of or reach a pH of 8.3. So why is that now? The acidity, I guess we are going to obviously develop the equation later. So again, in the earlier particular, what is it now, mineral acidity, we only try to look at the strong acids present, and which certainly would have to rule out H2CO3. In this case, phenolphthaline acidity, right, we are going to go a bit further. We are obviously going to measure all the strong acids present. We are also going to measure H2CO3, right? We are going to measure H2CO3, but obviously not HCO3 minus. So in this case, we are going to look at all the strong acids, right, and then H2CO3, and thus we need to come up with an endpoint that will help us measure that when we titrate your solution or our solution against a base, right? Let's look at what it is. So here we are trying to measure what do we say, strong acids obviously and H2CO3. So this is what we are trying to measure, right? So let's just look at the relevant graph once and let's see how we can do that. So H2CO3, right, as you see, this is the profile for H2CO3, and this is the profile for HCO3 minus, and this is the profile for CO3 2 minus, right? So let's look at this here, and you see H2CO3 is still in considerable quantities until around this point. So if I want to measure all the H2CO3 minus, I titrate until this particular what do we say, pH with the base, right? I keep adding a base until I reach which point now, this particular point. And why is this point? Because you want to exhaust all the H2CO3 present in the solution, because you are trying to measure H2CO3. So obviously in this region, what am I measuring? I am measuring all the H2CO3 present, and obviously if there are any other strong acids present, they are going to be titrated here in this region as in this pH, right? So now the key is that if you look at this particular equivalence point, your H2CO3 is not the reference anymore, but HCO3 minus is the reference, right? So when we looked at your what is it now, mineral acidity, we chose our reference as H2CO3. But in this case, it's not H2CO3 anymore. We are trying to also measure H2CO3. The reference, you can think of the reference when you choose your components or try to understand the equation with respect to your acidity, that you are going to have the reference as HCO3 minus. So let's look at what the relevant equation will turn out to be, right? So let's go back here, and now acidity. So obviously you need to measure all the strong acids. So let's say I'm using H plus to understand them, because all the strong acids are going to reprotonate, and I am also going to measure the concentration of H2CO3, right? These are the acids that I am going to look at, right? These are the acids, and I need to subtract the bases. So bases are going to be certainly OH minus, because if it's the pH is high, you need to look at the relevant acidity, right, or the effect of high pH on acidity. That is why you are obviously going to subtract the base, and obviously any other what is it now, bases. And in this carbonate system, what are the other bases that are present? So obviously CO3 2 minus, not HCO3 minus. Why is that? The reference here in this case is HCO3 minus. With respect to HCO3 minus, you are trying to understand the system, right? So here you are going to have OH minus minus CO3 2 minus. So those people who are following it keenly, you might ask, or the question might arise in their minds. So if you look at the equation for mineral acidity, we looked at, I think, -2 times CO3 2 minus, but why aren't we looking at, or why don't we have a coefficient of -2, and only why do we have a coefficient of only -1 here in this particular phenolphthaline acidity, right? So the key is that earlier the reference was H2CO3, so CO3 2 minus can take 2 protons, right? But in this case the reference is only HCO3 minus. So let's say if we think of it in terms of difference, right? It's not a true difference obviously. HCO3 minus and CO3 2 minus differ by only one proton, right? So earlier H2CO3 and CO3 2 minus, they differ by 2 protons. So that is the reason here, because the reference is HCO3 minus, we look at the coefficients from that point of view. So same case here with respect to H2CO3, because H2CO3 can only give out 1 proton before transforming into HCO3 minus, which is our reference, right? Or CO3 2 minus can only take 1 proton before transforming into HCO3 minus, which is our reference, right? So this is where our coefficients come from, 1 H plus for H2CO3 because it can donate 1, and -1 here because CO3 2 minus can take 1 H plus. So that's the relevant equation here, H plus H2CO3 minus OH minus and minus CO3 2 minus. And most people end up using or trying to calculate phenolphthaline acidity. Why is that? Again, most people end up looking at this particular acidity when people talk about acidity. Why is that? Because we are trying to measure all the H2CO3 and the strong acids present, which in effect means you are titrating to a value which is 8.3 here. Obviously it's slightly higher than pH 7, but around, or still nearby the pH 7, right? So that is the reason people usually look at let's say this phenolphthaline acidity, because it will give you an idea about the natural systems, their ability to neutralize a base if you go till around pH 7, or in this case obviously pH 8.3. So, but obviously, as with our background, let's say with our fundamental background, we know there is one more level, right? And that's going to be the total acidity. And why is that? Because you still have CO3 2 minus present, or HCO3 minus present. So in the next case we are going to look at, which is the total acidity, we are going to look at CO3 2 minus as the reference and also measure HCO3 minus and H2CO3, right? Again, before we go further, just to understand the system, we said the reference was what now? HCO3 minus. Let's try to look that up, pardon me, try to understand how we arrive at this, right? And what are the different species? H plus, OH minus, and what else? CO3 2 minus, HCO3 minus, and H2CO3. And how many H plus do I need to form? 1 H plus 1, and obviously 0 here, and here it's going to be -1 and 0. And how can I form HCO3 minus? By 1 HCO3 minus and -1, and thus you see that particular coefficient here -1. And how can I form HCO3 minus? Just 1 HCO3 minus and no role for H plus, right? That's why we have no term here with respect to HCO3 minus. Again, the key is that HCO3 minus here is our reference here. And why is it that we are looking at HCO3 minus as the reference? Because the equivalence point needs to be around 8.3, so that we end up measuring all the H2CO3. So they are interlinked obviously. And how do I end up measuring H2CO3 in terms of the components, or expressing H2CO3 in terms of the components here? So 1 HCO3 minus and 1 H plus, and that's what you see here when you are writing it as where is this now? H2CO3. And so obviously H total in this case will be what now? H plus minus OH minus minus CO3 2 minus plus H2CO3, right? And again, thus in this case is going to be similar to this equation, as you can see, and obviously only when you choose HCO3 minus as your component, right? So that's the key. Earlier we chose H2CO3 as the component, and then the relevant equations are going to be different, and HCO3 minus here is our component or the reference, and that's why your H total equation is going to be different, right? So next step, so here we are going to measure total acidity, right? And the pH is 10.5, so obviously we need to understand why we are going to look at 10.5, right? That's obviously the key here. So we are going to go back to that. So again, keep in mind that some people also think of phenolphthaline acidity as total acidity, but that's not strictly speaking, it is not true. So there is something else called total acidity, right? Again, acidity, we are looking at base neutralizing capacity. So what does that mean? We want to sum up all the acids that can neutralize a base. So earlier we looked at strong acids. The next aspect we looked at was strong acids and H2CO3, And next aspect which we are going to consider now obviously is, by logical understanding or analysis, we see that it's going to be strong acids H2CO3 and also HCO3 minus. So what do we end up measuring here, right? We end up measuring strong acids, or we want to measure the strong acids, we want to measure H2CO3, and we also want to measure HCO3 minus, right? And this is what the total acidity gives you an idea about. So let us now go back to the figure and see why a pH of 10.5 is necessary, right? But the key obviously is you want to also measure HCO3 minus, right? So earlier when we are trying to measure H2CO3, right, we end up titrating until that point or until that pH when all the H2CO3 would be consumed, which approximately turns out to be 8.3. But obviously if I am also trying to measure HCO3 minus, so what do I need to go to? So obviously 10.5 I guess, right, or 10.7, right, around this particular value. What was the value given? Okay, 10.5. So people end up measuring or going to 10.5, right. So again keep in mind that we are not measuring all the HCO3 by minus, but more or less most of it, right. So anyway, that is the key here, and that is the reason we end up choosing what do we say 10.5 I guess, right. Pardon me, here it is not here, it is somewhere out here I guess, right. And obviously the reference here is that it is going to be CO3 2 minus, right. Let us look at the relevant equation there. So the reference is going to be CO3 2 minus, right. And what next please? We are trying to write down the equation here, acidity, and that is going to be equal to all the sum of the acids. So it is going to be H plus 2 times H2CO3, and why is that? The reference now is CO3 2 minus, and obviously 1 times HCO3 minus, right, and minus OH minus. And obviously what is this, as you can see, is the total acidity, right. So let us try to understand this in terms of our components once. So what is the reference here? It is CO3 2 minus now, and H plus obviously is always our component. So let us try to understand the system from that point of view. So we have what do we have here please? We have the relevant species, they are H plus, OH minus, H2CO3, HCO3 minus, and CO3 2 minus, right. And so H plus 0 and 1, 0 and minus 1, and how do I come to H2CO3 1 and 2? Because 2H plus 1 CO3 2 minus would end up as H2CO3, and that is what you see here. And obviously the key is that now the reference or the component is CO3 2 minus. But with HCO3 minus, what do you see? It is going to be 1 here and 1 here, and here obviously it is going to be 1 and 0. So obviously H total in this case is concentration of H plus minus OH minus. So we are just summing up this here, H total, right, plus 2 times of H2CO3 plus HCO3 minus, right. So that is the case we look at, yes. And so thus in this case obviously as you see this equation, when you write up H total and with the unit with the components of CO3 2 minus and H plus, you will end up with a H total that is similar or the same as total acidity, right. So again we looked at 3 aspects, one for strong acids, one for strong acids and H2CO3, and the last one for strong acids H2CO3 and HCO3 minus, right. Again why HCO3 minus? Because it can also neutralize a base by donating 1 proton and transforming into CO3 2 minus, which is its deprotonated form, right. So let us move on. I believe we are going to look at the effects of addition of acids and bases. So we looked at this in the context of what is it now, our alkalinity. So here let us look at a particular equation, let us say, and then try to understand that. So let us say we are going to add, let us say, first an acid, right, and then second we are going to see a case of adding a base, and then third case we are going to look at addition of carbon dioxide, right. So what are one of the equations? I guess let us see if it changes for different cases. It strictly speaking should not. So let us take total acidity for now, H plus, right. What is total acidity? Let us work it out for one case. Total acidity is equal to what now? H plus, and what are the other acids present? 2 times of H2CO3 plus HCO3 minus, pardon me, right, minus OH minus, right. So, if you add an acid, right, if I add 1 equivalent per liter of acid, right, how is that going to transform the equation? So, I am going to end up increasing my H plus. So, that means when I add acid, it is going to end up increasing my acidity, right, by 1 equivalent per liter. So, now let us move on to our particular case of the base, and what are we looking at here? So, base we are adding, if I add 1 equivalent per liter of base to my solution. So, what is the total acidity or acidity going to, how is it going to change? So, here by adding a base I am going to increase the OH minus concentration. So, in effect what does that mean? I am bringing down the value of the total acidity, right. So, that is what it means. So, when I increase the concentration of the base present here, or add a base to the solution, so the initial acidity will come down, right, or will decrease. And how, I guess, if I add 1 equivalent per liter of base, I am going to have 1 equivalent per liter of my particular acid, right. So, that is the case. Again, we need to understand that acidity is nothing but base neutralizing capacity, right. So, if you end up increasing the concentration of your acid, what does that mean? You have more compounds that can neutralize your base, but obviously if you are adding a base, right, an extra load on your system, so thus you are decreasing the acidity or the ability to neutralize a base in your particular case, right. So, let us see with respect to CO2, let us just try to apply that in this case. So, obviously we know that CO2 can dissociate into H2CO3, right, in the gaseous to aqueous, right, and H2CO3 we know can either go to, what is it now, H plus HCO3 minus, or it can also dissociate to 2H plus and CO3 2 minus, right. Right. So, let us say if I add 1 equivalent per liter, let us see what the effect is going to be. So, if let us consider this case first, right. So, H plus is going to increase and HCO3 minus is going to increase, yes. And so, in this case, if for 1 equivalent per liter, let us say increase, the total acidity though, the total acidity is going to increase by what is it please, units of 2, right, 2 equivalents per liter. Why is that? So, if it is just H2CO3, you see there are 2 units here, and if it is dissociating into H plus and HCO3 minus, you see that there are H and HCO3 minus 2 units. So, that is 2 equivalents per liter. But obviously, if you look at the equation for let us say phenolphthaline acidity though, and what was that equation? Let me remember that or try to just analyze that here. So, the reference is HCO3 minus, right. So, it is going to be the first the acids present, reference is HCO3 minus H2CO3, right, minus the bases present which are OH minus and CO3 2 minus. But for phenolphthaline acidity, how would your particular system change, right? This is phenolphthaline acidity, not total acidity, right. How would the system change when you add carbon dioxide, right? We know that total acidity changes by 2 equivalents per liter. So, CO2 can dissociate into H2CO3, right. So, obviously, if I am adding more CO2, what does that mean? The phenolphthaline acidity would change by or increase by 1 equivalent per liter. So, when I increase CO2, right, by 1 equivalent per liter, the total acidity changes or increases by 2 equivalents per liter, but the phenolphthaline acidity would only increase by 1 equivalent per liter. Again, so we looked at various aspects, right, until now, the three kinds of acidities, and then we started discussing about the effects of acids and bases. Just to refresh your memory, right, if you remember that with respect to alkalinity, which looks at the acid neutralizing capacity, right, we saw that when we bubble carbon dioxide through the solution, the acidity does not change, right. And why is that? The key was that with respect to alkalinity, we had a particular set of definitions that we tried to understand, right. As in, when we put in H2CO3, it dissociates into either H plus or HCO3 minus, which in that alkalinity equation cancel each other out, or can further dissociate into 2H plus and CO3 2 minus, and again cancel each other out because we need to look at the equivalents, and CO3 2 minus has a equation there. I mean, let me write this down here. Where can I write this down? Okay, I will just try to, what did we have with respect to alkalinity? The definition was OH minus, right, plus HCO3 minus. So, all the bases plus 2 times of CO3 2 minus H plus. So when we bubbled carbon dioxide through it, what did we see? Carbon dioxide can go to H2CO3, right, which can dissociate into HCO3 minus plus H plus, and also further to H plus and CO3 2 minus, right. So if it stops at this step, you see H plus and HCO3 minus, they cancel each other out even though they are produced, yes. And if it goes to complete dissociation, you see that 2 H plus are given out, right, minus 2 there, and CO3 2 minus 1, but you have a coefficient here, so again they cancel out. So whenever you increase carbon dioxide concentration or bubble it through your water, there is no effect on alkalinity, right, it is still a constant. But that is not the case here when we look at acidity. And why is that? Obviously, you know, we have different cases here again, for one for what is it now, the total acidity, and one for phenolphthaline acidity, and so on. So obviously for total acidity, when we look at the relevant variables, you see that when you add carbon dioxide, we notice that it increases by 2 equivalents per liter, when carbon dioxide increases 1 equivalent per liter. But for phenolphthaline acidity, if you look at the relevant variables, you see that it only increases by 1 equivalent per liter, right. So we are done with discussing alkalinity and acidity, which are remarkably important aspects in natural and engineered systems. So in the next class, we are going to look at the applications, right. And we are going to heavily look at using Vimintic again. And with that, I will end today's lecture session, and thank you.